Oceani, Shesh, and Vinay. Ammonia is getting quite a lot of attention in the marine industry. We will go through a brief background of ammonia as bunker fuel and possible solution to scale it up. SCM is a leader in providing engineered solutions to the offshore, marine and energy industries. SCM executes projects through 4 business units: rigs and floaters, specialized shipbuilding, repairs and upgrades, and offshore platforms. SCM have innovation focus on renewables, gas, ocean living, process and drilling, and digitalization. SCM targets to have 30% of the company turnover generated from sustainable product solutions by 2025 through its Sustainable Growth Vision 2025. SCM is actively involved in ammonia projects, one in Norway, one in Singapore. In Norway, world's first green ammonia tanker is being designed by SCM subsidiary Lng Marine. In Singapore, a consortium of MOL, SCM and Itochu recently obtained an AAP for ammonia bunker vessel. There is an emphasis of decarbonizing maritime sector to support the climate action. The maritime decarbonization pathways include policy intervention, technology intervention, and capacity building. Along the technology intervention pathway, cleaner fuel switching is one of the options. LNG is the cleanest fossil fuel as on today. In the context of current energy transition sought by the European Commission, it represents an excellent alternative to reduce greenhouse gas emissions and help combat global warming. There is also a recent introduction of carbon neutral LNG in the market. Carbon neutral LNG does not mean that such cargoes does not generate emissions during the production or transportation, but that associated carbon footprint is measured, verified, and offset through the acquisition of carbon credits. LNG can be an effective transition fuel as there is a considerable reduction in CO2 emissions, around 30%, twice the reduction in NOx emission and no SOx emissions, but the methane slip concern still exists. Another promising option is the electrification. Electrification plays a major role in the transition, combined with clean power generation. Electricity share in final energy expected to reach about 35% by 2050, compared to less than 20% today. Electrification may be a good solution for shorter distance vessels, but longer distance vessels need alternate solution. Talking of biofuel, another alternative fuel, recent Indian ethanol policies and blending targets for biodiesel in Indonesia and Malaysia are responsible for most of the growth in Asia. India is set to become the 3rd largest market for ethanol demand worldwide by 2026. The concern is biofuel scaling up production comes at a threat to food security. Hydrogen and ammonia are major contenders for next major alternate fuel. Hydrogen has the potential to be a powerful enabler of this transition, as it offers a clean, sustainable, and flexible option for overcoming multiple obstacles that stand in the way of a resilient and low carbon economy. Liquid hydrogen is carbon neutral, carbon free, and GHG free. Refueling time is a major aspect when it comes to bunkering. In that aspect, hydrogen fuel is comparable to diesel. Ammonia, on the other hand, is an effective carrier of hydrogen. The existing ammonia consumption focuses on fertilizer. However, given that it emits no CO2 when consumed, it is gaining in energy sector visibility. Though combustion of ammonia doesn't emit CO2, but possibility of NOx emission, especially from engine application, exists. Also, in terms of handling, storage, and transport, ammonia is more mature. The refueling time is comparable to oil today. In terms of LCA emission, both hydrogen and ammonia depends on the production pathways. Current hydrogen and ammonia supply chains are carbon intense. Ammonia has a huge potential as an alternate fuel. Ammonia, when compared to LNG and LH2, can be stored as a liquid at room temperature, which makes it an attractive option for transport and storage. Ammonia is not new. Hundreds of millions tons of ammonia is annually produced. Ammonia's volumetric energy density is broadly half of LNG, similar to methanol, are higher than hydrogen, making onboard storage economically feasible, albeit not as compact as the heavy fuel oil used today. Hydrogen requiring cryogenic tanks maintained at -253 degrees Celsius, while ammonia requires less cooling and can be stored at temperatures of around -33 degrees Celsius. In terms of heating value, ammonia is still lower compared to LNG and LH2. To deliver the same energy content, ammonia requires 2.5 times more volume flow. Ammonia has high LFL, which means we need to supply additional source of heat. In ammonia engines, the chemical reaction rate is slow than traditional fuels due to its high ignition temperature and low flame velocity. Also, it is the reason for ammonia discharged from the exhaust without burning. While designing ammonia bunker vessel, some key aspects to be considered are like the multi-gas carriers today carry ammonia worldwide. Understanding the synergies will help in efficient design. Ammonia is toxic, hence suitable safety considerations to be made in the design. In terms of environmental impact, ammonia can cause significant damage to the environment when exposed. The design should have consideration on this factor. Talking about bunkering operation, the LNG bunkering experience is a key for ammonia bunkering operations. the designs that include common aspects from LNG bunkering. The compatibility of bunker vessel with terminals, FSUs for loading, and with receiving vessel for bunkering to be checked. The receiving vessel can be a fully refrigerated or fully pressurized or semi-pressurized and fully refrigerated carrier, depending on the design. The design synergies with multi-gas carriers are: multi-gas carriers follows IMO's IGC code. Ammonia bunker vessel is expected to follow the same. The multi-gas carriers today carry a range of liquefied gases such as LPG, ethylene, LNG, ammonia, etc. The LPG carriers today are more suited for conversion to ammonia carrier bunker vessel. Some of the materials used in LPG tanks and systems would also be suitable for the use with ammonia, so the vessel can be easily retrofitted. The appropriate material selection shall be made similar to MGC design. Clause 17.12 of IGC codes addresses stress corrosion cracking. Copper alloys with nickel more than 6%, aluminum, zinc, galvanized surfaces are not compatible with ammonia, which is also followed on MGC design involving ammonia. Ammonia can be cooled by several types of cargo cooling plants existing in MGC today. The ammonia is transported today with atmospheric pressure gas carriers or semi-pressurized gas carriers. The ABV can utilize the learning for containment selection from these MGC design. Please note, for bunker vessel, the bunkering operation and flexibility also contributes to the type of tank selection. Another safety criteria from MGC that can be adapted in the design is not to use the inert gas that contain carbon dioxide for purging vents and hoses. The design interventions. Ammonia is a toxic, corrosive, hardly inflammable gas with a strong characteristic odor. The odor threshold is between 5 to 50 parts per million of air. Ammonia although causes no chronic effects to the human body. It can be extremely irritating to the eyes, throat, and breathing ways. Acute and chronic exhaust toxicity to aquatic organizations is very high. Venting in the vicinity of ports is a safety and environmental concern. So, gas detectors, safety shower eye wash at appropriate locations, pH meters, ammonia scrubbers in the exhaust, swill combustor, are few mitigation measures that can be included in the design to address the above concerns. Few observations from earlier studies on ammonia release and dispersion point of view are as follows. Pressurized ammonia has potential for much larger release, flashes when released, and forms foam. Ammonia foam is denser than air. Refrigerated ammonia, while on the other hand, will form pool with limited release rate. Evaporation rate depends on the heat from the surrounding. Evaporated ammonia is more buoyant and disperses better. The ISO 20519 and ISO 18683 is considered more relevant for ammonia bunkering. The credible approach and LFL distance are not relevant for ammonia. Risk-based approach should be preferred option. Toxicity and major discomfort to be considered. In brief, we need to perform a typical facility risk assessment of the bunkering site and establish inner, middle, the outer exclusion zones in addition to the hazardous area. Ammonia bunkering can in principle take place in many different ways. Ship-to-ship transfer of refrigerated ammonia by hose, truck-to-ship transfer of pressurized ammonia by hose, tank-to-ship transfer of pressurized ammonia by loading on. For deep sea shipping with significant amounts of fuel to be bunkered, a bunkering ship, that is ammonia bunker vessel, would be the preferred solution. STS introduce high operation flexibility, can be deployed quickly in different locations, and can bunker different capacities. Simultaneous operations like cargo handling is also possible. The LNG industry experience on ship-to-ship transfer can scale up the ammonia STS operations. The ammonia bunkering operating procedure is expected to be similar to LNG bunkering. The sequence is like pre-transfer operations, followed by planning on cargo transfer, and a cargo transfer happens, and there is a post-transfer unpurging, followed by disconnection, and there is a vapor balancing done before unmooring and reporting on the STS. The bunker vessel and the ship to be bunkered must have necessary equipment and installations to bunker safely. The typical components of a LNG bunkering are fender, hose or saddle, emergency release coupling, vessel separation detector device, quick connect disconnect, hydraulic power unit, hose handling crane. The basis for STS to remain the same. The connection sequence for a ammonia bunker vessel will be a ammonia bunker vessel manifold to ERC to hose to a QC-DC female to a QC-DC male to the receiving vessel manifold. The LPG hoses designed for fully refrigerated cargoes down to -50°C can be deployed for ammonia STS readily. With the above design and the operation synergies with existing multi-gas carriers, LNG STS bunkering, we believe ammonia bunker vessel provides a flexible solution for scaling up ammonia bunkering. Thank you all for your attention. We thank the organizer of this conference for the opportunity. Any questions, comments from the audience is welcome.
Thank you. May I know whether this presenter is online? Okay, yes. Hi, hello, hello, hello. So, yes, thanks for the presentation, and hello colleagues from Sembcorp Marine. Now on the floor we have some participants, and also I'll see any questions to Pigeonhole as well. Any questions or comments? All right, please. By the way, is it clear? Hello? Yeah.
Yeah, we can hear. Yeah.
Sure. Okay.
Okay, thank you for the presentation. I would like to understand one thing is related with the comparison between LNG and ammonia. We understand that the bunkering process of LNG and ammonia are quite similar, but in terms of the safety-wise, right, CH4 is treated as safer, but ammonia is really, really dangerous. So even though right now we haven't solved the issue of methane slip, so if let's say ammonia is taking place, right, what do you think that we can actually solve the issue of ammonia slip, and also how can we address the concerns that public may have over the safety issue? Yeah, thank you.
Yeah. So this is a major concern existing today on ammonia. Methane is more flammable, whereas ammonia, on the other hand, is toxic. So when we talk about ammonia bunker vessel, we are talking about toxic gas release. And to tackle that, the most relevant approach is to have the safety protection in place. As compared to any other LNG vessel, we need to have a similar approach adapted to a bunker vessel. And we are not talking about a new fuel. Ammonia is being transported worldwide on multi-gas carriers. So there are existing safety protocols to be followed for any kind of ammonia release on board. So talking about a bunker vessel, we are talking about a vessel inside a port. So there is a difference between a cargo vessel and a bunker vessel. The bunker vessel is located inside a port. Yes, there is a concern associated with the release of ammonia with respect to the vicinity of the port, and that the public response should be included in this case. But currently we are trying to address this problem in our bunker vessel design. The most appropriate way is to reach out on a risk-based assessment, and we are trying to implement as robust safety measures as practically possible on the bunker vessel. Apart from that, the public opinion of having a ammonia bunker vessel in the vicinity of a port and the effect of release of ammonia, accidental release of ammonia in the port is to be studied.
Yep. Chin Hui here. Okay, maybe I can add a little bit like what Kumar mentioned. We follow the risk-based approach to identify the potential leakage during the bunkering operation and during the transfer of the cargo. Okay, in terms of design, right? Compared to LNG, they got some specific requirement on the material selection because the ammonia is different as compared to the LNG in terms of the composition. Then we also have a different requirement on the gas detector and also the piping design. So when we talk about piping design, we will need to have more the double wall pipe in place to eliminate the potential source of leakage. Yeah, this is some so-called area we have identified during the hazard we have conducted with vendor and also all the stakeholders.
Yeah. Yep. Hope we answered the question.
Okay, thank you.
So that's good. Okay, so I think then that's all for now. Thank you so much for joining us online, and please stay with us. And to remind everyone as well, you can post your questions on Pigeonhole, all right, for online participants as well. Okay, thanks again. Let's put our hand together. Thank you.
Thank you.
Thank you.
Thank you.